here, are you all planning on taking the GRE, GMAT? You? Hey, Deepak, how are you doing? Okay, so, okay, 1 second. All right, so we've got 3 here. We're starting recording, so I think we can get started. So we are going to be talking this week about one of the more annoying categories of quantitative question on both the GRE and the GMAT. This is a type of question that tends to show up in more difficult areas. All right, not always. It's like, you could be tested on sort of the the basic fundamentals of this stuff. And like a median level question, but for the most part, this kind of falls into the category of the miscellaneous, more advanced stuff. This kind of goes with probability, so say combinations, probability, sequences and series. Sometimes things like maybe standard deviation. These topics tend to be, what they call like the miscellaneous advanced topics. So depending on how you are doing currently on the GRE or the GMAT, you might want to figure out how much time investment to put into a question like this. All right. So for example, if you're on the if you're taking the GRE and you're getting around, say, somewhere in the 150s, somewhere between like 145 to 155. This is probably not the kind of thing that you want to focus too much attention on until you start to move your score up a little bit more, because you're not going to see these all that often, although they will show up. So it's like, I'd say this kind of question is probably going to be like, around only 5% of the tests. All right. So maybe, maybe one question, if you're doing average, say maybe, up to say, 2 or 3 if you're doing well. On the GMAT, same kind of thing applies. If you're getting around, say, anything kind of sub 600 or something like that, I wouldn't worry about these too much yet until you start to really kind of score consistently in the in the 600s, 700s. All right, because the thing is, you really want to kind of invest most of your time in the things that are going to show up a lot. Things like algebra, things like word problems, things like number properties, that kind of thing. That said, because we're actually going to focus on these today, we are going to devote a good amount of time to it. So I'll probably do about 30 or 40 minutes of content, and then these are short classes, and then we'll I'll open it to questions if anybody has them. Okay, so to start out, first of all, how to recognize a combinatorics problem. When we talk about combinatorics, we are really, it's kind of a fancy way of, these are the factorial problems. All right, these are the ones about counting. All right. So you want to be aware of kind of the kinds of questions, the kind of phrasing, right? It's going to be like, how many ways, right? How many arrangements? Right? How many different whatever, that kind of thing. All right. You want to be aware of a few different things. So to start out, let's start out with the kind of the fundamental counting theory. All right, so if you just have if you've got something to the effect of sort of kind of 3, well, let's say a few completely independent situations, like, how many ways can you say choose, we'll say an outfit. If you have, say, 5 pairs of pants, right? Let's say 3 shirts, right? And say, I don't know, 4 pairs of socks, all right? Let's throw some ties in 6 ties, right? With 4 pairs of socks, all right? Let's start with something really straightforward. The whole idea of counting is basically, you can say, the whole idea of this is that everything gets kind of grouped with everything else, right? Because nothing affects anything else, all right? So for each pair of pants, you could also potentially, pick any of three shirts and any of 6 ties, right? Any of 4 pairs of socks. So for these kinds of things, you're going to multiply. It's going to be straightforward: 5 times 3 time, and I'm treating the pair as 1 for this kind of thing, times 6 times 4, right? But nothing restricts anything else, and then whatever that happens to be. You can do the math if you want. All right. That's the fundamental counting principle. And you can also kind of map it out to kind of see why that works, right? I'm not going to draw the entire thing out, but it can help to visualize these kinds of things. So what do we have? We've got, 5 pairs of pants. Let's draw a few of them. Again, I'm not going to draw the whole thing. All right. 1, 2, 3, 4, 5. Okay, so for each of these 5, right? Okay, these are the pants, right? Then the next column is going to be your shirts, right? Okay, so then the shirts, it's like, well, okay, fine. So here we've got, 1, 2, 3, but those 3 shirts could be duplicated all the way across, right? So you can imagine doing like a tree diagram. 1, 2, 3, 1, 2, 3, and this is why you multiply. This is why you do 5, times 3, because each one of those 5 is going to have 3, times 6, because each one of those is going to have 6. So you end up, these things balloon pretty quickly. 5 times 3 times 6 times 4. All right, that's kind of the fundamental idea. Now when we get into things like arrangements, let's take a look at something like this. Let's imagine a horse race. And here's where we're going to get into the factorial stuff. All right. Let's say we've got a horse race with 8 horses. Okay, we're going to start things simply. All right, so we'll start with the randoms. Okay, how many finishing combinations, including all the horses, no restrictions at all, how many ways can I arrange these horses? How many ways can they finish? And I'm actually going to draw it out, because actually drawing it out for smaller numbers can be useful. All right, so let's do like a 1, 2, 3, 4, 5, 6, 7, 8. All right. Okay, so we got 8 exclamation point. For anyone who's not familiar, you guys should be at this point, but if you're not, review it. We've got 8 factorial, so 8 times 7 times 6 times 5 times 4. Now, let's think logically what that actually means, and then also look at kind of how we're going to do that formulaically. All right. So what we're really saying is how many ways can we arrange or permute, all right, the horses in a race. All right. So how many arrangements, permutations, are there of 8 horses? Okay, and that, as we've got here, 8 factorial. Okay, 8 factorial, which really means 8 times 7 times 6 times 5 times 4 and all the way down. Why is that? Well, we can really kind of envision that from the fundamental counting principle over here. So basically, we have got an unlimited number. Well, not unlimited, but we can use any of those 8 for the first slot. But once we have that, then we've locked everything down. All right, we've locked down the 8th slot. We've only got 7 horses left. Right, so if you imagine that there's 1, 2, 3, 4, 5, 6, 7, 8 in that first slot, now for the second slot we've only got 7, 3, 4, 5, 6, 7, and so on down, to 1, right? So you end up with 8 times 7 times 6 times 5 times 4 times 3 times 2, so you have the 1 lone straggler, right? 8 factorial. Okay, the formula, if you want to call it that, for just basically permuting something, is simply going to be n factorial, right? Where n equals the number, a number of things that you want to permute. You want to, let's say, arrange. Use kind of more a colloquial language here. Okay, the next version of this, and here's where you start to, you're not going to see something like this on either the GRE or the GMAT because it's too straightforward. All right, even in like a, it's possible that it has like a low level question, but usually it's going to be something a little bit more, it's going to be more involved. The next level up is where you talk about subgroups. All right, so here you probably see the term order matters or order does not matter. Be aware of whether matters or not? Okay, what do we mean by order matters? A lot of people see this and get confused. The idea is, do we need to count each arrangement separately, or do we need to count them all as the same? All right, so if horse 8, if the horse name is just a number, right? Is 876 the same as 768? Is it the same as 687, or do we want to count them all independently? All right, so that's where we need to figure out whether we're talking about order mattering or not, and that will tell you whether you're talking about arrangements or groups. All right, so say I wanted to do something like how many top 3 finishing, how many top 3 finishers or finishing arrangements can there be in this 8-horse race? Okay, so for this kind of thing, you want to look for clues. Arrangement is a clue. That tells you that each arrangement needs to be counted independently. All right? Okay, so the way you do this, let's say, well, okay, we need the top 3. So what we don't need is anything below that. So let's kind of draw our race out again. 5, 6, 7, 8. Okay, how many top 3 finishing arrangements? Order makes a difference here. All right, so when order makes a difference, it means you're dealing with permutations. Order matters. All right, so this is an arrangement question. So when you're doing that, we're going to say, well, okay, we start out the same. All right, it's like you still have any of 8 horses that can fill the top slot. Okay, now we got to figure out who's in second place. 7. Who's in third? 6. But then you're done, because all the different ways of arranging the bottom 5 don't matter. We don't even want to think about them. We want to ignore them. All right. So it's simply going to be 8 times 7 times 6, and then you're done. All right. Now, what that looks like formulaically, there's a couple ways. Some of you may have seen this expression, NPR. Is anybody familiar with that? And what that basically means is how many ways can you arrange an R group size out of N total items. All right. Now, what that looks like as a formula, you start with your N factorial, but now we have to restrict it, because now we need to divide through by everything that you don't want to count. All right. So things in the denominator basically kind of help to restrict. All right. So that's going to be N factorial over N minus the group size factorial. So what you're doing, so here you end up with 8 factorial over 8 minus 3 factorial, all right? So what that leaves you with is simply 8 times 7 times 6, because factorials will cancel all the way down, right? Because in the numerator you have 8 times 7 times 6 times 5 all the way down. In the denominator you have 5 times 4 times 3. So all of those below 6 will cancel out. All right. Now, all right. So why does this work? Well, what you're really doing, you're saying, well, let's we're going to take out the group. The group size is 3. All right. So we're going to N minus 3, 8 minus 3. That's going to give us 5 left. Everything in the denominator, we are canceling out the stuff that we don't want to count. So you can imagine that everything in the denominator is kind of redundant. All right, does that make sense? It's kind of one way of thinking about it. So if you have stuff that you don't want to count, divide it through a denominator. I'll show you some more examples of this in a minute. All right. Okay, so we don't want to count those bottom 5. It's going to be 8 minus 3. So you end up with this. Okay, the next iteration of this is something called combinations. This is where the order does not matter. All right, this is where we're talking about group size. All right, so up here, order matters. This is arrangements, also known as permutations. All right, the next one is going to be combinations. So if order does not matter, you have a combination question. And here it's really a matter of saying, we don't care about we don't want to count each individual arrangement. It doesn't matter. We just want to count each group as one. All right. So let's go back to the horse race here. All right. So say you've got, okay, 1, 2, 3, 4, 5, 6, 7, 8. And these will be phrased a little bit differently. Say we have something like this. Say you have something like, out of an 8 horse regional race, only the top 3 can advance to the state qualifying rounds. How many groups of top 3 finishers can advance? Okay, this is a little bit different because the thing is, we are not talking about, 876 and 768 and 687 as being different. Here we're saying, okay, I just need the 3 best. I don't care how they're set up. We're going to take the 3 best. You think about like Olympic qualifying trials and things like that, right? You can take the top 8 and send them on to the next round. It doesn't matter if you finish first or you finish 8th. All right. So for this kind of thing, this is a question where order makes a difference. Sorry, where order does not make a difference. Order does not matter. All right. So the equation, well, actually, let's do it first. You can start with this 8 times 7 times 6 because it's still a group size of 3, right? You can stop it here, but you also don't want to count all the different ways that you could potentially arrange those numbers. So if you could potentially arrange these like this, 6, 7, 8, 6, 8, 7, we only want to count this as 1. All right. So how do you do that? Well, you're going to divide it again by this redundancy factor. So what that's going to look like is going to be n factorial. It starts out the same with these things. We're n minus r factorial. All right. But now you're going to take the group size itself and divide through again. All right. So what's going on here is this is, the total. This represents the redundant values of everything, below, right? So that's redundancy. Right with a mouse here. Redundancy for everything below. Everything below 6, if that makes sense, right? And that is the redundancy of the group size itself. Because you don't want to count all 6, you only want to count it as 1. Redundancy of group size. So essentially what's going on, we're saying, okay, we've got n factorial to start out, that's unrestricted. Then we're going to say, well, let's divide that by our 8 minus 3, which is 5 factorial, right? So 8 factorial over 8 minus 3 factorial, and then 3 factorial. All right. So what that ends up looking like is 8 times 7 times 6 over 3 times 2 times 1. All right. That's the first group of things. Now let's go and take a look at a question. Remember, whenever you've got some kind of redundancy, you're going to want to divide. You're going to want to put it in the denominator. So let's take a look at how that works in practice. Okay. I'm going to give you all, I don't know, maybe 30 or so seconds to take a look at this. And keep in mind, in terms of general strategy for both GRE and GMAT Quant, give yourself a fair amount of time to read the question carefully and determine whether it's a question that you're comfortable with. All right. If it's something that you're like, oh, I think I know where to go, then yeah, give it a shot. But don't spend too much time, right? If you, On the GMAT, you're going to have an average of about 2 minutes per quant question. On the GRE, you're going to have an average of about 1:45 per quant question. All right. So if things start to get, a little bit over, it's fine. But if you're at about like, two minutes and nothing is falling into place, then at some point you need to say, look, I don't want to spend 5 minutes on this question. I'm going to move on and, focus on the, equally valued ones that I'm more comfortable with. Again, keeping in mind that this is meant to be, more advanced content. So tackle it if you're, if and when you're ready. All right. So going to this one, spend a little bit of time thinking about it. How many 4-letter words can you pick from abracadabra? We'll talk about this in a couple of minutes. I should specify, I'm not talking about actual words here. It's being basically a word being any 4-letter combination, any 4-letter grouping. Now, when you see a question like this, you want to, basically make sure that it actually is, one of these types of questions. This is actually a, sorry, I realized my camera's not even half the cost to figure that out. Okay, what are some clues to kind of tell you what it is? Well, we've got a how many, right? So we know it's a counting question. We know that 4 letters is either going to have to do with combinations or arrangements, right? Groups or arrangements. We need to kind of figure out which of those is going to be. We need to figure out what kind of restrictions do we have here, all right? So, well, how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8. There's 11 letters, all right? So probably a good chance that we're going to have an n value equals 11. What do we do with this, though? It's not just going to be 11 factorial, right? Because if it were 11 factorial, that would not count for, it wouldn't count for the 4. It's like, what do we do with that 4? It also doesn't count for the repeated letters. We've got repeated A's, right? We've got 5 A's, I think. 1, 2, 3, yeah, 5 A's. 2 B's, and 2 R's. We need to think about what we're going to do with this. Okay, so the first thing I would say, well, this is actually, it's both an arrangement and a group question. All right. Okay, so the first thing is, well, okay, let's start out. Say we were to go in, like, and just take our 4-letter words without thinking about any restriction at all. That would be the first thing, right? Because ABRA and ARBA, those are 2 different things, right? Okay, so that would be our 11 factorial over 11 minus 4 factorial. We'd start out there, all right? And that is basically the second example that I was showing you. That is basically this one right here, right? And that's the example where, where order actually makes a difference. All right. So that's where you start out. Okay, so we're going to end up with 11 factorial over 7 factorial. But we're not done. Because now we have a situation where, although order makes a difference for the first, part of the problem. So let's take our ABRA, right? So ABRA, we could hypothetically arrange those in 24 different ways, right? A, R, B. There's a lot of ways of doing this. But there's a problem, right? So that would be 4 factorial, right? 24 ways. There's a problem, though. And the problem is that we've got some repeated letters. And we don't want to count those repeats. We want to, so whenever you've got a repeat or redundancy, you want that to go in the denominator. So what you're going to do, you're actually going to say, well, we've got 5 A's, so we don't want to count 5 times, all right? All those potential ways of arranging those A's, we don't want to count them, 5 factorial ways. We don't want to count them one way. So you're going to divide through by that 5 factorial. We also have the same thing with B's, So it's like whether, whether that B is there or that B is there, it doesn't matter, right? You don't want to count it multiple times. 2 factorial. The same thing with R. 2 factorial. All right. Now, keep in mind the GMAT, neither the GRE nor the GMAT are meant to be computational. So you're not meant to be, doing multiplication with large numbers. So they, especially given that the GMAT doesn't give you a calculator, So if you had this kind of question on a test, it would basically, the answer would probably be in this form: 7 factorial, 5 factorial, 2 factorial, 2 factorial. And then maybe you would, divide that 7 factorial into the 11 factorial to simplify it a little bit, but it'd be something on this idea. All right. Okay, let's do some others. Let's see here. Oops. 1 second. I'm going to stop sharing the screen for 1 second while I track down this problem. I guess not. I'll show the screen. Okay, next one we'll take a look at is okay, let's take a look at this one right here. Okay. Now I'm going to see. Cover up the answer here. Nah, okay, so ignore the explanation down here and focus on just this stuff right there. All right. Okay, now think about this one. It is very easy to take a quick look and say, oh well, this is going to be just the fundamental counting principle, right? It's going to be your basic 4 times 5 times 6. But the thing is, wait, that's not quite right, all right? Because we're only talking about we have a group size. We've got a restriction here, all right? How many ways can you arrange 5 ways codes to 6 caps? We're saying that, oh wait, we've only got 3 men for each thing there. All right. Okay, so what's really going on? We need to figure out our arrangements first of all for the coats. They skip a step in the thing down there. All right, so what you really have for that first thing is like, well, how many ways can 3 men wear 4 coats? All right. Well, that's going to be your 4 factorial over, remember, 4 minus 3 factorial. That's how they get this. All right. So that's going to be your first arrangement, right? So it's like, okay, so we figure out how many ways we can distribute the 4 coats among 3 men. All right. Okay, now we need to multiply. Okay, so we have 5 waistcoats for 3 men. Well, then you're simply going to have your 5 factorial over 5 minus 3 factorial. And then the exact same thing for the 6 caps. And this ends up being a high number, so again, you would need to actually probably would need to actually multiply it out 60 times 120. All right. Okay, some other things to keep in mind. They will sometimes group things. All right. So you need to figure out whether or not you need to kind of treat people as a group. What you need to lock down. Let's take a look at some examples. Say you have something like this. Say you've got 5 students, and they are filing through the door of a school. All right. So you have student 1, 2, 3, 4, 5. Okay. And then you'll have something like, oh, I don't know. Okay. second. How many ways can 5 students enter a school if Jill and Bob are at the end of the line, and Bob are at opposite ends of the line? All right. So you guys have all, if you've been studying this for any amount of time, you start to see, they keep coming up with more and more creative ways of coming up with these restrictions. All right. So it's like, oh, okay. What does this mean? Well, normally it would be simply, 5 times 4 times 3 times 2 times 1, right? Which would be 120. But we've got a problem here. We've got some restrictions. What does it mean? How does it affect the problem if Jill and Bob are at opposite ends of the line? And again, for small numbered things like this, it can't hurt to, just draw it out. So if Jill and Bob are at opposite ends of the line, we don't know which ends those are at, right? So we could imagine we've got Jill and Bob like this. We could also imagine that we've got Jill and Bob like this. We don't know. But what we do know is that Jill and Bob are locked down, but nobody else is. That means that we arrange not 5, but 3. So here it's going to be, so instead of being, it's going to be, n factorial over, n minus r factorial. That's fine. But the thing is, the n is no longer 5. The n is now actually going to be 3. All right. So you end up with 3 factorial here. All right. So 3 factorial for the first one, which equals 6. The problem is that's not everybody, because there's ones where Jill is first, and there's one where Bob is first. All right. Well, when Bob is, so here we also have another one. And basically, because we're taking all of these circumstances plus all of these circumstances, you're going to add them all up, right? Which is going to be 3. Sorry, it's going to be 6 plus 6 equals 12. Another way of imagining it is saying, well, wait a minute. So I could say, well, let's see, I've got 3 factorial, because I've got one way of arranging the 3 in the middle there. I've also got 2 ways of arranging Jill and Bob, right? So you can do it that way as well. Gives you the exact same thing. All right. They might complicate it another way. They might say, okay, how many ways can 5 students enter a school if Jill and Bob have to be standing next to each other? So for something like that, oops. Let's copy and paste this one here. Same kind of thing, but then they've got a variance. Like, well, okay, Jill and Bob are standing next to each other. Well, you can visualize, right? So you can say, well, wait a minute. Okay, I still have some information with which I could sort of lock down Jill and Bob, and I don't know anything about the other 3, right? So then, I could say, well, so what's going on here? Well, if Jill and Bob have to be standing next to each other, there's basically, they could be in that spot, or they could be in that spot, or they could be in that spot, or they could be in that spot. There's 4 possible ways, right? Plus another, because, Bob could be first. There's actually 4 plus 4, right? There's actually going to be 8 possible ways of arranging Jill and Bob. And now I still need to commute the other 3, right? So that's going to be 8 times 3 factorial equals 8 times 6 equals 48. All right. Okay, I'm going to give you guys a problem that is sort of modeled off of this. It's got a couple variants. So let's take a look here. Let's say you have a table. Let's do a different color for a change. We've got a table, and we have got 8 chairs. These are chairs. 2, 3, 4, 5, 6, 7, 8. Okay, now here's a question. It's larger. Eight people, 4 men, let's say 4 boys, 8 people, let's say 8 kids, 8 people, 4 boys and 4 girls are seated around the table. In how many ways can they be arranged if they have to be seated alternately? As in boy, girl, boy, girl. All right. 8 people, 4 boys and 4 girls are seated around a table. In how many ways can you arrange them if they have to be seated alternately? All right, so you can have 2 boys sitting together, you can have 2 girls sitting together, and they could be alternate. How would you do that? You guys have a little bit of time to think about it. A couple things to think about. What have we got? It's like, well, we know that, okay, how many ways can they be arranged? We know that we're dealing with arrangements. We know that we probably have to figure out how to, excuse me, how to deal with that 4 and 4, right? Now, here's the way I would think about it. The arrangement of boys and the arrangement of girls are independent of each other. One has nothing to do with the other, all right? So one thing that you could do is say, well, wait a minute. How many ways can I arrange 4 boys around the table? So let's say I start with a boy here, which would mean that the arrangement would be like this. All right. Okay. Well, if that's the case, you simply have 4 factorial for the boys arrangement, which is 24. I would multiply that by the completely independent, because the girls are on different chairs, they're not on the same chairs, right? So because they're on the chairs next to it, they will get their own factorial. All right, so the girls will be 4 factorial. So that would be 24 times 24, 24 squared, which equals 576. But we're not quite done. And the reason that we're not quite done is because we don't know who's actually sitting at that first slot. We know that, if we start with a boy at the top chair, the first chair, then, we'll have 4 factorial times 4 factorial. But we could also have a girl at that first chair, in which case we'd have another whole set of 576. Total of 1152. All right. Let's see. I think I'll do one more problem and then wrap things up. This kind of covers just the content. Find it. Okay. This is a tricky one that a lot of people get wrong, so let's talk it through. This is one from the GMAT Prep Club website. All right. So why don't you guys spend a little bit of time thinking about this one here. And while you're doing that, I'm going to start drawing things out. Okay. 9 people divided into 3 groups. Each group can only have 3 people. Okay. Bit of a clue here. We're talking about groups. Doesn't look like we're talking about arrangements. So we may have an order not mattering situation. At least for part of it. So what I would say, well, okay, basically the first one, you've got you basically, for the first group, you're just taking 3 out of the 9, right? So you're imagining, you say, well, okay, so, I need 9 times 8 times 7, but it's not actually 9 times 8 times 7. It's got to be 9 times 8 times 7 divided by 3 times 2 times 1. Right? Okay, so we got an answer for feedback. It's C, if I remember what the actual answer is. I believe it's, I think it's going to end up being a little bit lower than that. I'll show you in a bit. Okay, so for the first group, you've got 9C3, right? So again, that is really 9 factorial over 9 minus 3 factorial, 3 factorial. All right. Because again, we've got a redundancy here because 987 and 879, we don't want to duplicate count those. All right. Okay, that covers the first group. We're going to multiply that by the second group, but now we're only down to 6. 6C3. Because we've already got everybody in the first group accounted for. And the last one is simply going to be, one way of arranging the those 3 people, right? 2, 1. And then now there's another step though. 3C3, which next equals 1. There's one more step though. All right. The problem is that because we don't care how these groups are actually arranged, like this one could be here, but that could also be there, or it could also be there. All right. So we actually have a redundancy at the group level as well, which means that you need to multiply this entire thing, divide this entire thing let's call this 1. The whole thing would need to be divided by 3 factorial. That's a tricky one. A lot of people get that one wrong. They usually get it to this point where where you have the 9C3 times the 3 out of 6 times the 3 out of 3, but then they don't realize that you can actually you don't want to duplicate the way the groups are arranged as well. So I think the answer ends up being A280. I'm going to double check on that 1 second. Yeah, it's 280. That's a tricky one. Okay, so that is going to wrap up the general content. I am going to stick around here for about 10 or 15 minutes. If anyone's got questions as to kind of how to think about these things, how to do these things, feel free. I'll stick around for a bit. And yeah, thanks for sitting in on the class, and Happy New Year to everybody.
Steve, I had one question in that 11 alphabet part 1.
Yeah.
Can you go back to that question, Steve, that A, B, R, A, that 11, 1 to the right?
Sorry, I'm not hearing you well today for some reason. The connection's not great. Do you want to try the chat?
Yeah, sure.
You had a question about the 11 letter one. Okay. Let me move over to that. Okay. Yeah. What's your question?
Yeah. So my question is, Steve, are you able to hear me now? Better?
I can hear you a little bit. It's kind of anyway, let me
let me just increase my voice here. So is it better now? Is it better?
Yeah, I think it's on my end more than your end. So I can hear you some, but it kind of fades in and out a little bit. That's one thing. It might be a little better if you use the chat.
So Steve, I could not understand this part here. Like when we are selecting from 11 letters, we are selecting 4. Then how come? So there will be cases where all 4 A's can be there, and then some B's can be there. So how did we actually decide on doing this particular part 11 factorial by 11 minus 4? I could not understand.
Because okay, you've got a couple of different things going on. First of all, it's like, okay, you need to restrict it first, or so how many 4-letter words? Okay, so for 4-letter words, the order doesn't matter. The order doesn't make a difference. The order does make a difference to start out, right? Because for any group of 4, you could imagine arranging them in any of in any different ways, right? So basically, you would need to kind of factor in all of the which is why you start out with your 11 factorial, right, over 11 minus the group size, right? So if you can imagine, if we're doing it, kind of using the horse race drawing, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Like, well, okay, 11 times. We can start with with anything for for the first any of those 11 letters, right? Times 10 times 9 times 8, right?
Okay.
So that's where you start. All right. So that's where I got my my 11 minus 4, right? That's what this is. But the problem is you've got duplicate letters. So we don't want to stop there at just 11 times 10 times 9 times 8 because you've got duplicate letters there. All right. So we need to figure out a way so that we're not actually including those duplicate letters. So that's why I was saying, oh, well, wait a minute. We've got 5 A's, right? If you imagined, like an A as one word, that's only one word. It's not 24, right?
Correct. Agree.
So that's why you need to say, well, there's 5 A's. We need to divide through by those 5 A's that we're not going to count. Because when you divide through by 5 factorial, it means that you've divided through by the redundancy, so you're only counting it once. But now we also have a similar situation with the letter B and the letter R. Letter B, there's 2 of them. You don't want to count it twice. So it's like, well, okay, fine. Let's divide through by that as well. Because remember, whenever you divide through, you're making the entire value less. So you're not counting the things extraneously. And then we're going to do the same for the R's. A, B, R. And with that, whatever that ends up being, it's going to be your final answer.
Got it, Steve. I got it.
All right.
Thank you, Steve, and wish you a very, very happy New Year.
Sure thing. Same to you. And I'll see you in a couple weeks.
Take care.
Take care. Bye-bye.